latitude setting for storms. It sounds good. By this model, we should have, as long as we're inputting the exotic sediment, the shells are being locally homegrown, as I've said. The exotic sediment, which is just coming out of the mountain belt only, in this model, generally people think of it having a high input, possibly even an increasing input if the world is getting stormier for a period of time. And that should lead to a pattern like this. If we have all these winnowed out storm beds up here, you should see a big splaying out of these from all of the sediment that is bypassed or moved from this environment out into the deeper water. That seems reasonable. If you're getting rid of it up here and yet still supplying plenty of that sediment, it's got to go somewhere, so it should go down the ramp. So this would argue that we have a lack of finer grained sediments in the up ramp because we've got just so much more winnowing. And that we should get this big package of thin storm beds mixed with thicker mud and silt layers as we go down. The concretion is another part of the story. I may not have time to get into all those details, but in this model I would suggest maybe if we get concretions they should be more up ramp and not so much down. That's a bit of a complex story. In any case, most of the sediment is bypassing, but there should be a big whopping package of that stuff down slope from the splayed storm beds. But, you know, such a model fed right into the notion of the mosaic stratigraphy. Storms would have quite different effects in different spots, even fairly locally, and one should imagine to see a patch of very winnowed out skeletal material in one place and maybe mud somewhere else, rather than the kind of continuity that we see. And already I thought from that, there's a bit of suspicion to be cast upon this as the full answer. Because if this is true, why don't we see a bit more of a patchy distribution? Why do we see such continuous bundles of limestone as we do? So I argued for a different story. Not that the storms are not important. They certainly are, and they're doing winnowing and they're doing these things. My model instead argues that the limestone bands that we see in the Cope Formation are only partly the result of storm action, but more importantly, the result of lowering the input of sediment coming in altogether. This is where the starvation part comes in. We have storms, sure, they're ongoing. We can talk more about whether there were storms also in the muddy time, but we know there were storms during the time of deposition of those shelly limestones. But I think a critical further point to this is shutting the faucet down, keeping the mud and silt supply back. This model predicts, instead of having this big splayed out package of sediment downslope, that we may get a little bit for a ways, but in general it won't be so much because there just isn't much mud or silt to be bypassed. There can be some low bypass. In general, as we would come down into the basin in this analogy, this being the Seabury Trough, we should see it actually getting more sediment starved because you're getting it further away from the source of muds, and furthermore, it's further away from the source of a lot of abundant crinoids and other things that make sediment by skeletal remains. So one should expect to see something quite different. And again, to get to a little bit of the concretion story, you might expect to see more concretions because concretions are generally thought to be associated with sediment starving. So instead of having greater storminess or shallowing of the water, we might have, in fact, not less storminess, but a slight deepening or something else that is causing the supply coming out of those rivers to the east to diminish. That's the starving part of the model. So we have these two things, and we've debated them back and forth, and how would you go about testing one versus the other? You can see some predictions that each model makes, by the way. That you'd have winnowed shell beds up ramp and a big pile of stuff down ramp if it was all due to the storminess, and that you'd have quite a different pattern if it was due to starvation. We started tracing these things out. Just want to point out again what a cycle is. We're going to look in a little bit more detail at the limestone part, and then the forgotten part, which is the mudstone, siltstone part. Again, one thing to test is all the storm evidence just in the limestones? The one model would suggest all the storm evidence should be located mostly in limestone. You can see it. It's obvious that there is some there. But is it all there? Is there some in the mud too? And we want to look at a little bit about what those limestones are like as well. This is a complex diagram, probably too complex from a paper we just published. But what I'm trying to show here, and to me, I must step aside and say, what makes it so exciting to go out and look at outcrops? It's wonderful to see fossils. I've always loved that. Sedimentary structures. But really what captivates me is thinking about time. How much relative time is tied up in different parts of the sedimentary record. So what I've tried to do here is just show equal time increments along this axis and a hypothetical drawing of a Cope cycle. Here it starts out with a bundle of limestones with ripple marks that are very much like what you'd see. This is based on an actual one. And here's a second bundle marking the next cycle. Some people would make the cycle from the base of the shale to the top of the limestone. I make them, for various reasons, from the base of the limestone to the base of the next one. Okay. And if we look at it, I will argue that there's a lot of evidence that this little thin limestone package, generally a few centimeters thick, sometimes maybe 50, that's about the upper threshold, represents, if you follow my little lines out here, a great big part of the total amount of time of that cycle. So here, these little lines extend upward from these beds and go up, take them across to the time scale. I'll argue that perhaps as much as a third of the total cycle time is tied up in the little limestone bed at the bottom. It's time-rich, as I like to say. I'm emphasizing the shell-rich limestone. We'll come back to this part later. That's the main thickness, and I want to look at that too. Well, let's look at the limestone here and look at some of the features. And of course, if you've been with me in the field, you've heard me, like a broken record, if anyone knows what a record is anymore, saying these kind of things. But you know, you see them, they have a sharp base. Sometimes they show cross-laminations, ripple tops. There's no doubt storms had their influence on those. But if you look at the sediment inside them that's making them up, you might find some very surprising things, including the mixture of organisms that probably never really would like to live together. Organisms that actually like soft, mucky sediment mixed together, for example, with ones that prefer a hard, gravelly substrate. So already you're beginning to think, time averaging. There may be a lot of time. You look at the preservation of the fossils in there, too. It's quite varied and suggests that it represents many, many generations. We'll get back to that. I want to also point to this, and I've pointed this out to many people in the field. The more you go towards the Seabury Trough, to the deeper part of the Cope Formation, the more you notice that underneath a good many of these limestones, there sits a Precretion horizon. Now that is a little tidbit that even Ulrich never said anything about, and I think is a key part of the story. So that's just a picture of different lines. Getting to what you see at those limestones, perhaps I jumped the gun a little bit. You see a lot of different things. You see Sauerbiella, for example, which is what we call a snowshoe brachiopod. One that was probably adapted more for at least a little bit of mud substrate, not necessarily a lot. But you see them massed together. You see some limestones full of disarticulated bits and pieces of crinoids, echinocrinus. Or sometimes at the tops or in base, or even sometimes inside, you may find some longer pieces of stem. You see mixed beds with mixed types of fossils. And actually, we're working on this issue, mixed colors too. I think the mixed colors are something that people have ignored, but you find pink specimens of Dalmanella, you find black ones right next to them. These have undergone different histories. That's why they're different colors. And that shows us that we're mixing together multiple generations in these things. A lot of different things. So, and if you compare with the shales immediately below or above, you'll find, yes, there's some of these same fossils in there, but they're just much more concentrated in the limestones than they are in the shale. So the shale then doesn't become such a different environment. It's not hugely different in depth, well, water depth, but obviously it was a muddier bottom. And yet it has some of the same characters. But here's an interesting little twist. If you take, so this is actually an extremely conservative example, but we took some mudstones and just disaggregated them and sieved out every bit of shell that was in there. And we started to think, well, how much how much of this mudstone would you have to take away by winnowing in order to produce a thin shell bed? By this estimate, where we had 2 to 5 or 8% of shells in a big block of mudstone, the amount of winnowing required would be 3 to 5 meters, that's 15 feet, of compacted shale. Now, shale was originally mud on the sea bottom, and it was probably compacted by as much as 3 times. So 15 feet of shale that we see today would equate perhaps to 40 feet of mudstone. Just think of that. How much winnowing would you have to get to produce a typical little thin Cincinnati shell bed? The answer is a heck of a lot, an awful lot. You'd have to take out so much mud that there should be piles of the stuff down ramp in the Seabury Trough.